Yo, what's up everyone? Welcome to Electrochemistry Part 3. Today we're going to be talking about galvanic cells, and another name for galvanic cells is also voltaic cells, so you might see either one of the names being used in this video and in electrochemistry in general. So what is a galvanic cell or a voltaic cell? A galvanic cell is a mechanism that leverages redox reactions to produce electrical energy. In other words, it leverages spontaneous redox reactions in order to produce electrical energy. It takes spontaneous chemical reactions that occur and they leverage that to produce electrical energy or electricity. And we're going to see how this works in a little bit. So in order to see how this works, let's take a look at a redox reaction. This at face value just looks like a standard single displacement reaction. You have the zinc pairing up with the sulfate and the copper being on its own. But if you write out the net ionic equation, you realize that zinc solid is going to zinc 2 plus and copper 2 plus is going to copper solid. So copper is being reduced, the charge goes from 2 plus to 0, and zinc is being oxidized, the charge goes from 0 to 2 plus. So the essential idea behind a galvanic cell is to split up both of these reactions. So you can split up this big equation into two smaller equations known as the half reactions. And on one side you have the oxidation half reaction where electrons are being produced, and on the other side you have the reduction half reaction where these electrons are being used up. And so in a galvanic cell, all you're trying to do is separate the oxidation and the reduction reactions. If you can separate the oxidation and reduction reactions, the electrons move from the oxidation half reaction to the reduction half reaction. And all we have to do is provide some pathway for the oxidation reaction to happen and the reduction reaction to happen, and that produces a flow of electrons, and we call that electricity. And of course, this is all really vague. What is actually in these cells? Let's take a look at that. But I just wanted you to understand the broad idea of a galvanic cell. It's essentially just separating the oxidation and the reduction half reaction and providing a pathway for the electrons to move. So let's look at this in more specific. Remember, the oxidation half reaction was taking the zinc solid and turning it into zinc 2 plus aqueous and 2 electrons. And on the reduction half reaction, you have your copper 2 plus ions reacting with 2 electrons to produce copper solid. So to start out, let's have our zinc solid and let's have our solution of our copper sulfate solution. Remember, this one, in this reaction, it only shows the copper ions. But remember, if we're talking about the entire reaction, the sulfates are also included. In the net ionic equation, they're not included, but of course in the big reaction, they are included. And so in theory, you should just be able to connect these, and the zinc solid is going to lose electrons, and those electrons move through this line, through this wire, into the reduction half reaction, and they react with the copper 2 plus. But there are some problems. Once the zinc solid does react, or once the zinc solid does become oxidized, that zinc solid turns into zinc 2 plus. And that zinc 2 plus is in its aqueous form. And so you can't have a zinc ion being in a solid, it needs to be in some sort of solution. So we need to add a solution around this zinc solid as well. We have our zinc sulfate solution. Remember, our sulfates are still included in the overall reaction. So we need a solution around the zinc. On the reduction side, those copper 2 plus ions are gaining electrons to produce copper solid. And so where does the copper solid go? Well, you would need some sort of solid copper where the newly formed copper solid atoms can accumulate. So essentially what's happening is that there's this zinc solid, those zinc atoms, those individual zinc atoms, think of these as the zinc atoms. Those zinc atoms are separated from the big solid and they become zinc 2 plus and they go into the solution. The electrons that are given off from this reaction travel through this wire into the copper sulfate solution. And when they react with the copper 2 plus, they turn into a solid and they deposit on the big copper solid here. And the chamber, or if you take this flow of electrons here and you connect it to like a light bulb, you'll notice that the light bulb turns on. This flow of electrons is electricity. These electrons on their pathway to move from an area of high potential to an area of low potential, these electrons are able to do work. And that work is what turns on a light bulb, is what creates electricity. And so a galvanic cell leverages a chemical reaction to produce electrical energy. But now there's a different problem. As the zinc solid deteriorates more and more, and you have more and more of these zinc 2 plus ions being put into this chamber here, you have an accumulation of positive charges. Those zinc atoms or those zinc ions are all positively charged. So as you do this reaction more and more times, you have an accumulation of positive charge. And on the reduction half side, you have your copper 2 pluses. Those are being used up, so all you're left with are your sulfate ions. So you have an accumulation of negative charges on the reduction half reaction. So how do you counteract this? If either of your cells accumulates a charge that's too great, if this oxidation half reaction becomes too positive or this reduction half reaction becomes too negative, the cell stops working. The reaction doesn't continue. So you need some sort of way to balance out the charges. And the way you do that is by using something known as a salt bridge. In a salt bridge, you have like a U-shaped tube, where within that tube you have some sort of ion solution. In this case, you have sodium and chloride ions. And over here is a porous barrier. If this side gets too positive, then these chloride ions are going to migrate to this side of the cell, and it's going to go into this chamber. You're going to have chloride ions accumulating here to balance out those positive charges. And on the other side, if you have an accumulation of negative charges, those positively charged sodium ions are going to be attracted to that negative charge, and those sodium ions are going to accumulate on this side of the galvanic cell. So you have sodium ions on this side, and you have chloride ions on this side. And of course, this is on a need basis. If there's no need to balance charges, then these ions are just going to stay there. That's the whole point of this porous, barrier. If you need them, they can pass through. If you don't need them, they can't pass through. And just a little bit of vocab. The side where the oxidation occurs is known as the anode, and the side where the reduction occurs is called the cathode. So an anode and a cathode both make up a galvanic cell. And remember, in an anode, the oxidation reaction occurs, and in the cathode, the reduction reaction occurs. And that was it for galvanic cells. I hope this was helpful. I hope you were able to follow through with this example of a galvanic cell. I hope you understand how these electrons move around, why we need a solution and some sort of metal here. And yeah, I hope this was helpful. I hope you were able to learn something. Consider leaving a like and subscribing, and I hope to see you later. Thank you.